This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount.
Okay, welcome back. In today's lecture, I'd like to talk about parallel transport and the action for point particles. So generally, we want to figure out how, in our curved spacetime that we have been generating, how point particles move and behave. So back when we had flat space, we had Newton's laws, right? We have F equals ma. Ma is the A is the second prime derivative of our like position. And if we were chilling in free space, we would have no forces on us, and F would be 0. So that would consequently mean that we would satisfy this equation. Now, if the second derivative of something is 0, then that something is linear in time anyway. So this means that with no forces acting upon you, you travel in straight lines. Basically, what this says. We can gather that when we go to curved spacetimes, this is not going to hold. We're not going to travel on straight lines, as you well know. We on the Earth, even though so we are going to classically we consider gravity a force, so that F is non-zero, and then you can like move things about so that this equation doesn't hold. But for us, like if we're on Earth and the Earth is going around the sun, that's not a straight line at all. But we want to write things in a way such that gravity is not a force. It is part of this left-hand side of this equation, built into the acceleration rather than as a force on the left-hand side. So we need to think about how we're going to do this. Okay. So let's go back and just think about flat space. If you are on a straight line, then you would go just like this between 2 points. Okay, so in terms, if we define your vector or your velocity vector to be the derivative of your position with respect to lambda, where lambda is the parameter that's just parameterizing this trajectory. You can think of it like time, but it doesn't have to be. Okay, so at any point you have a vector like this, and you can kind of think about, we can help our velocity at one point kind of tells us how to get to the next point, in that we follow this arrow. Okay, so what that means is that at this point, this arrow is going to be exactly the same. And it's exactly the same at every point. That's what it means to move in a straight line. Okay, so that means that spatially, if this arrow is the same everywhere, that means the derivative of our vector at any point is going to be 0. Well, specifically, it's along the direction of motion, so we have to, if we want to make it so it's along the trajectory, we just dot it with this velocity vector, as that's always along the trajectory. Okay, so to reiterate, what I'm saying is the velocity vector should not change spatially along the direction of motion. That's what this statement means. And this will be a very good equation for us to base stuff off. But we can immediately see the problem. If you watched the last lecture, I basically spent the whole lecture complaining that this thing was not a tensor. It doesn't transform like one when you act on vectors or tensors. So what we're going to need to do is when we go to curved spacetime, we're going to need to modify this equation to get something different. And that's going to lead to a different definition of parallel transport than what we have here. Okay, so in the last lecture, what we discussed was the modification to this partial derivative that made it transform like a tensor, and that gave us the covariant derivative. So to recap, the covariant derivative of any vector, where by this I really mean the components of the, once we take the derivative of the vector, this we found was equal to partial derivative of the vector plus some correction term. So this is going to be mu, and then sigma like that. Okay, Now, visually, or this breakdown into two sums is actually very, very, very useful. Okay, so first, this first part kind of tells us how our vector field changes at every point. So let's say if I had a hill, if I'm looking like down on top of a hill, and I put different particles here. So if I put a particle here, then it's going to roll this way. If I was to put a particle here, then it was to roll this way, and so on. And this kind of gives us a vector field, right? At every, if I was to push a particle in each direction on the field, they would carry on down the hill like that. For this vector field specifically, this term is non-zero because if I go to different points in space, I get a different vector. So obviously the components of the vector are going to change with respect to the space as I move around. So that's what this term gives us. When we were deriving the covariant derivative, you may remember for this second term that we had the following relation. When we took the derivative of the basis vectors, we found that this is equal to the following, right? In that the covariant derivative acting on basis vectors gives us these Christoffel symbols times the basis vectors. So what this tells us is that this term tells us how the basis vectors change as we move from point to point. So let's say we're on a sphere now. So it's kind of going to look like this, right? If I have a basis vector on this sphere, we can see that even if I was to parallel transport this, so that is, I go along the trajectory and I inform my next step of the trajectory by the current way my vector is pointing. But remember, this has to, it's on a if it's on a curved surface, it has to stay on the surface. So this is going to follow a trajectory that goes down and around, and in each point, this what was a basis vector, and still is for this space. Compared to our Cartesian way of looking at this, vector is completely changed place, right? And that's reflected in that the derivative is non-zero. Okay, so this term tells us generically how the vector field changes as you go to different points in space, and this term tells us how the basis change. Okay, which is very important. And on curved spaces, we see that basis vectors are not do not stay the same. Okay, so we then have two problems. We have, so the equation we wrote down was the following. Okay, and this had two problems. It was not a tensor, and it did not account for how the basis vectors change as you move around a curved surface. Well, both of these are solved by the same solution. We get this equation and we replace the regular derivative with the covariant derivative. Okay, and generically, this will be how you do incorporate a lot of things into curved spacetime. You get the first derivative and you replace it by the covariant derivative. This happens a lot. And it's just because it accounts for that extra change in basis with this term that you would see that you end up getting for moving on curved surfaces. Okay, and you can prove mathematically that this is how stuff parallel transport. If you go to a sphere and you solve this equation for the coordinates on a sphere, you will find that this will trace out a great circle, like the same circle that you get by going around the Earth at the equator. If you were to just travel in a straight line. Okay, so we can take this and apply it to get it in a form that we had for f equals ma. Okay, so let's say we're on a trajectory x, which is parameterized by some parameter lambda. Then we can take the derivative, and that's going to be our velocity vector. Okay, then we can plug it into our new equation, which we said that was going to look something like this. Okay, so that means dx mu d lambda, and then we'll expand it out using this expression. So partial mu, and then we're going to plug in this expression here, so that gets a nu d lambda plus dx sigma d lambda gamma nu mu sigma. Okay, and then now what we can do here is this thing here, because this is just dx nu d lambda, and then this is partial derivative dx mu. This can actually be recognized by the chain rule. If you're to do the chain rule now, this is the same as d lambda d lambda. Yeah, it's basically two derivatives. So that's going to be basically the second derivative of lambda. Okay. I think I discussed this in one of the earlier lectures, but you can see this because lambda is a function of x, of all the coordinates x, and again it ends up like that. Okay, so these two terms just turns into a second. Sorry, wait, hold on. No, this is just one derivative. Turns into two. The second one comes from in here already. Apologies. Okay, so yeah, those in a sense you can kind of think of just canceling these, and you get d over d lambda. It's kind of the index notation trick we've been using. Okay, so that first term, because this is d lambda, this is d lambda, you get second derivative of dx mu squared, and plus dx sigma d lambda, and then dx mu d lambda, dx mu d lambda, and then the Christoffel symbols, nu mu sigma. Okay, now if we were to use time, then each of these lambdas would be t. Then this would look exactly like if we can do the classical test of if we set our Christoffel symbols to 0, do we recover our flat space? If we set these to 0, we're left with second derivative of x squared is equal to 0, and that's exactly the same equation we have for flat space. So we can see these terms that were added with the Christoffel symbols that account for the curvature. All right, and if you want to go backwards, you can move these to the other side and then interpret this as a force in line with Newton's equations. But we want to do it this way. This is what we want to work with in GR. All right, and then one last thing, parallel transport. So I said that this is for a vector parallel transporting itself. But you can also have one vector w parallel transporting another vector v, is when this is true. So basically you're saying along the direction of w, the vector v does not change. So just as a quick example for what that means for later. If I'm on a circle like this, then I could have my equator here. My vector v could be the vector that points up here. My vector w could be this one. To parallel transport v is to literally just move v along like this, right? Because along w, which is along this direction, I'm saying that the components of v do not change. And that would go all the way around and then you get back to here and stuff. All right, so having discovered a law similar to Newton's law in curved spacetime, we would like to do one better. We know, or you may know if you've studied classical mechanics in details, that Newton's law can only take you so far in solving certain problems. Often it can become, especially for the equation we had, which had multiple indices, meaning there was multiple equations going on, and these equations can become quite coupled and quite difficult to solve. The solution to this in classical mechanics was to reformulate into something called Lagrangian or Hamiltonian mechanics. And that's what we'd like to do for our curved spacetime. Okay, so in Lagrangian and Hamiltonian mechanics, we think about what trajectory the particle will take between 2 points, right? Because initially it seems there are many, many trajectories that one could take, and we just have the problem of finding out which one it is. Okay, so the thing that is positive is that the trajectory that ends up being followed by the particle is the one which extremizes, that is, maximizes or minimizes some quantity, which we call the action. Okay, now specifically, we formulate this in a way such that so each of these trajectories depends on two things, all right? So there's the position of the particle, or the coordinates it has along the trajectory, which are different, and which I'll denote Q. And you can also think that there could be two trajectories that follow the same coordinates, but they could be going at different speeds. So they may also depend on the time derivatives of these quantities. Okay, and so the action is for the whole trajectory. If we want to distinguish between trajectories, it is very useful to think about there being some quantity L, which depends on these Q's and Q's dots, and that we integrate this, and we just use time, classical mechanics, to parameterize these trajectories, and then we integrate this, we add up at every point this quantity, and it is the sum total of this for the whole trajectory. So we integrate from A to B, then we would integrate from A to B, kind of dope. Okay, so this quantity is known as the Lagrangian, and then what you can do is you can do a variation. So this is a delta because this is a functional derivative for this, because this each of these trajectories of function, and you have to find the function that minimizes this action, not just like the value that minimizes that function. Okay, so when you do this variation, I'm not going to go through it all, but what you find out for this Lagrangian is that it must behave the following differential equation. So the time derivative of dl dq dot minus dl dq is 0. All right, and then a quick demonstration. So we can actually you can figure out by looking at stuff that if you were to choose the Lagrangian, that is the kinetic energy minus the potential energy, so just be a half q dot squared minus u. Typically u only depends on the position. There's issues if it depends on the velocity, like unconservative type of stuff. Okay, then if we apply this equation, we can see that dl dq dot, so this is L, dl dq dot is equal to mq dot, and dl dq is equal to minus du dq. That is correct. Okay. So what that means for us is that the time derivative of mq dot minus, and a minus there, so plus du dq is equal to 0. So if I was to move that to the other side, we see that mq double dot is equal to minus du dq. Now you may remember from classical mechanics that we can recognize the derivative of the potential with respect to the coordinates. This is the negative part of that. This is just the force. So what choosing this Lagrangian to integrate over and then extremize for our action gives us back exactly, well, this is just ma, exactly, it gives us back our Newton laws. So this is an example of how think can be reformulated in this way. And then this equation often is a lot easier to solve in different scenarios, because directly dealing with energies can be easier than the specific ones. Okay, so we would like to do this for curved spacetime. So we're going to need to come up with an action principle that reduces to the equation of parallel transport that we saw earlier. Okay, so when coming up with an action, it can be very hard to know where to start. And the best way to do is just to think, I have a particle, it's in curved space-time, it's going between 2 points. What are the quantities that are relevant here? If we think of constants, well, maybe with the mass of the particle, we want to be in a relativistic theory, so we're going to need the speed of light c, and maybe possibly we might need g because gravity is curving the space-time, but we don't know yet. Then we can think about the particles. Well, if they're just 2 particles in space, well, we can maybe have a position vector x1 mu and x2 mu. Okay, that's kind of about it. We can think of stuff, but then we need to think about what does our action satisfy. So there's going to be 2 things that must satisfy. So we saw that the action is just a scalar quantity. It's just an integral of another scalar. So it's not going to have any indices or anything like that, which means it's covariant. And that makes sense. We would imagine that if we change coordinates, the action shouldn't change value, or that might mess up where it is extremized, and that wouldn't make sense. Okay, so it's going to be covariant, and there is another one that is specific to curved spacetime. This is something I haven't talked about too much, but you may know from from special relativity that different observers moving at different speeds, so they're in different inertial frames, perceive time differently. Okay, so what that means is if I have 2 trajectories, if I parameterize it with lambda, or I parameterize it with another one t, and t is not equal to lambda, these 2 trajectories kind of amount to thinking about going along this trajectory at different speeds, which picks out different observers. Okay, we don't want to do this in general relativity. We want to talk about stuff like the action that doesn't pick out a specific observer and a specific time. So what we want is reparameterization invariance, in that it shouldn't matter what lambda we choose to parameterize our trajectory, they should all work the same. Okay. Invariance. Okay, so we're going to see if we can use both of these to construct an action. Okay, well, so covariant, that means if we want to construct a quantity, it's going to need to be a combination of variables that are contracting. So we can kind of take our 2 vectors and then, oh yeah, we obviously forgot to mention the most important one, of course, that being our metric. That's obviously going to play a part in trajectories. It's going to be dependent on the distances between points. Okay, so we could do something that will turn out to be very naive. We can say, okay, well, we have vectors, or more relevantly, okay, we could say, you know, the distance between them, and then the only way to make a covariant quantity out of this is contract it with the metric. Okay, this is kind of like what we did with proper time. But then we run into a very big issue. Our metric, when we make stuff curved spacetime, depends on position. But which position do we use? Do we use x1 to evaluate their metric at? Do we use x2? If there's an ambiguity, it means we can't really do this. What we're implicitly doing here is we had some origin. We're comparing these two vectors, which are at very, very different points. This works fine when I'm on a board and it's in flat space, but in curved spacetime, as I said before, we simply cannot compare points that are separated. Okay, so that's no bueno. So how can we solve this? Well, what we know we can compare are points that are infinitesimally close together, and that actually works well with the concept with the action leading to the Lagrangian. So we want to consider something along our trajectory. Okay, so first of all, I'm going to parameterize the trajectory by lambda. Now, by my second rule, I'm going to have to show that that's invariant later, but I'm going to write it like this. Okay, now I can stick in a quantity like this in here if these points are infinitesimally close together. Okay, now that I've also introduced this lambda, I kind of have a new quantity I can add to my thing, being the derivative, or possibly higher derivatives, of our positions. Or these are just the vectors, basically, of the particles. Okay, then okay, well, maybe we could take these derivatives and we could make a combination out of them. Okay, so let me, for sake of brevity, set this point to the origin. Okay, so then we would just have dx1 minus 0, minus 0, so we don't have to worry about that. Okay, and then I'll just relabel that to dx. Okay, right, well, I could do this. I could have my velocity vector with respect to lambda, d lambda. Okay, that looks good, that's invariant. But the problem is, or that's covariant, but what about reparameterization invariance? Okay, so the idea would be that we could change from lambda to some other parameter t. Okay, then we could do the chain rule. So dx mu would go to dt, dt d lambda, d mu would be affected. Then it would dx nu, dt, dt, d lambda. And then I also have a d lambda here. That's no good, right? Like maybe cancel one of those and then I have a dt, but then I still have this term here messing things up. So this is not parameterization invariant. What's a way to fix that? Slap a square root on there. Now when I slap a square root, these are all in the square root. So you can see I have this term twice. So when I pull that out of the square root, I just am left with one of them. dx mu dt now. Still got that metric. The other one. And now we just have dt, d lambda when it's pulled out, and it's d lambda. Chain rule, cancel those. And now I just have the exact same action, but parameterized by t instead of lambda. So this is reparameterization invariant. Very, very nice. Okay? And you can convince yourself that there's no other combination of all these quantities that gives us exactly this, which is pretty cool. All right? Okay. I rubbed out the constants there, but we're going to need them. Okay, so then we can figure out the units really quick. Okay, so the action has units you can check of angular momentum, which I know that that's like 4 cross p. Yeah, so that's length by mass by length per second. Okay, so what do we have here? Okay, so to figure out the units, you can check that this thing is unitless, and then lambda is just parameterizing your trajectory. So we can choose that to be length. So this overall thing has unit length. So we have this covered. Then we just need a mass and then a velocity. That's perfectly covered by these two. So we can just multiply this by mass and by c. And it's very convenient to also have a -1 there. You can check. And this gives us our full action. Okay. So what you can actually check is you can, it's a nice problem to check the non-relativistic limit. So that's kind of the limit of in flat. So first you go to flat space, so you send the metric to the Minkowski metric, and then you take the limit as c is going to infinity. That's kind of the classical limit and or non-relativistic limit, and you actually recover the same action we had earlier of a half mv squared. So this is first free space, so we wouldn't have any potential. So you would actually recover the same potential up to a constant term, which you can ignore for the action because it doesn't come into the Lagrangian equations of motion. Okay, so this is very useful. Now, there's one thing we can actually notice is that this quantity looks very similar to something we had earlier. So if we have square root dx mu d lambda mu mu nu dx nu d lambda. So we can kind of cancel these because there's two lambdas in the square root. We can cancel them. This is kind of just like dx mu g mu nu dx nu. Now this quantity, if we can actually recall all the way back to lecture 2, is the same as the line element squared. So essentially our action is minus mc integral of the line element along our trajectory. So our action is minimizing our distance, or so kind of space-like distance in the case of 2 points that are spatially separated, or 2 points are time-like separated in that you can, or 2 events, not really points, if you can get from one event to the other event without going past the speed of light, then those trajectories extremize the proper time along that trajectory. Now, I said extremize, so it would be nice to figure out, is that minimize or maximize? And that's a good question, which we can answer following the argument. Okay, so let's say we have some trajectory between 2 points. And I'm going to argue, pick one and see where that, pick one of these 2 choices and see where that leads me. So I'm going to say, okay, the proper time is minimized along these trajectory. What one can then do is remember that light rays, which if this is like a Minkowski diagram, this is just in flat space, this is just a thing to do with flat space that also carries true to curved space-time. Light rays will go at 45 degrees. Okay, so if I was to have a ray of light that is to zigzag, well, I can get that trajectory to zigzag arbitrarily close to my trajectory. If I just keep increasing the number of turns, then this is going to approximate my curve eventually with an increased number of turns. Okay, then I can remember that in the limit, as your velocity goes towards c, your proper time gets increasingly small, right? Now, it's a little disingenuous to say that your proper time is 0 at the speed of light. It's just that our theory doesn't properly describe then. But what it means is you experience time slower and slower and slower as you go along a trajectory that goes at the speed of light. So what this means is that our trajectory is always infinitesimally close to a trajectory that has proper time 0. So there is no way that our trajectory could minimize proper time. It must be the opposite. It must maximize proper time. And that's a very, very cool fact. You can use it for lots of things. One example would be you can use it to solve the twin paradox. So the twin paradox is we have 2 twins born, one stays at home, we send the other out in the spaceship. because of special relativity, they go really, really fast. They're going to experience time dilation and then come back, and they will experience time slower. But the paradox comes from the fact that it's hard to tell these apart from the perspective of the twin who goes on the ship. It's the other twin that has gone away from them, and then they come back. So to that twin's perspective, maybe that twin that stayed on Earth should have been younger. And so it's hard to figure out which twin, when they get back, is younger and which one is older. To solve this, you notice that the twin who stayed at home is the only one who is on a trajectory that was free of forces, because to go on the ship you had to do those forces. So what we can say is that this twin who stayed at home must satisfy this action, and they must be maximizing proper time. And that tells us for definite that it is the twin who stayed at home who is older when we get back. So that's a cool little consequence of that. Okay, so now that we have our action principle, we want to see if we can solve the equations of motion using the Lagrange equations we wrote down earlier, and see if we can get back to the equations of parallel transport that we had earlier. Okay, so we know our action is going to look like the following. Mu dx lambda dx nu lambda mu. Okay, so one thing, before we had q and q dot. So in our case, it's going to be, we're going to have x mu and x mu dot, which is going to be equal to just dx mu lambda. Okay. We then write down Lagrange equations up here in the corner in terms of what we have now. This is what they're going to look like. All right, this is all we have to solve. Now, before we do this, this square root is going to make things quite tricky. So we're going to notice something really quick. So when we take the variation of the action, that's the same as taking the variation of our Lagrangian. Now, well, I can notice that actually, well, I can write my Lagrangian as square root of g, where g is just what's inside here, okay? Now, when I take a variation of this will be the same as the variation of g, but this variation is just like a derivative. So what that's going to give me is actually, when I take a derivative of square root, x power a half goes, I'm going to take away 1. Sorry, that's going to be, it's going to go to this, okay? The variation is going to give me this. Now, I'm setting this to 0, which means I'm going to set delta L to 0, so this thing is equal to 0. If this is equal to 0, that equation is actually equivalent to delta G equals 0. So, to make my life a lot easier, I can minimize the action that has G, delta x mu, delta x lambda, dx nu, dx d lambda, and then G mu nu, d lambda. So this is the action prime, but because of this thing, this action will lead to the same equations of motion. And that's what we're looking for in this case, the equations of motion. Okay, so let's use this. This is going to be what we're plugging in as L up here. So the left-hand side is going to tell us d lambda of, and we need to figure things out. So these are both x dots. So this is going to be d x dot mu. And then we need to be careful not to repeat indices. So it's quite clear that the metric won't depend on these x dots, and likewise these x dots won't depend on the coordinates. So let me make this alpha. This is mu x dot nu g mu nu. No, sorry. Yeah, no, that's fine. Okay, and then minus derivative with respect to this. So now these won't depend on the coordinates, so we can just take them outside. It's just going to be derivative alpha of the metric that comes out there. Okay, so this is what this equation becomes. Okay, right, so let's expand out this bottom term. It's going to be, first let's do the inner derivative. We're still with d lambda on the outside. When we do that inner derivative, okay, we're going to get dx dot mu dx dot alpha. These are only true if these two coordinates are the same, because this is the same quantity. So this is the same as d mu d alpha. Then when we do this for the chain rule, by the chain rule we get one of each quantity. So we're going to be left with 2, and then we just need to be careful. So alpha is going to be equal to mu in the first one, and alpha is going to be equal to nu in the second one. But if we relabel indices, we'll get the same one. So essentially, we get left with alpha and a g dx. Hold on. Let's do it out properly so I don't mess things up. So one of the terms, so the first term will give us x dot nu d mu alpha d mu nu. Yeah. So that would make the mu. So that would give us 2 x dot nu, and then the mu and the alpha are the same. So the alpha is there, and the nu is contracting. Okay, that's good. So that gives us what's inside there, and then it's just minus this x dot nu, the alpha nu. Okay, then we just have to take the derivative of this. Okay, so we're going to get 2, then x double dot nu, g alpha nu. Then on the second term, we're going to get 2 x dot nu. Then we have derivative of g mu nu with respect to lambda. On this one, we can use the chain rule, so that we get so d lambda is equal to dx mu d lambda d dx mu. Okay, but we have to be careful to not use the same index mu. So we can write this as, this is just x dot with a beta, and this is d beta g mu nu. Okay, then that is minus this term. Mu x dot nu the alpha d mu nu. Okay, now these are all looking very similar. These just x dots just don't quite have the same indices of these, so we're going to mess around with them a small bit. Okay, I'm going to take this term and I'm going to split it up. So I get into 2. So x dot nu, x dot beta, d beta, g mu nu, plus the same term, because there's 2 of them. So I can just split it up like that. Beta, d beta, g mu nu. Okay, then what I'm going to do is I'm going to change, because I'm summing over nus and I'm summing over betas, I can swap them on one of the terms. All right, let me just double check. That's okay. I'm worried, uh-oh, I've lost a mu somewhere. So before this term, this one has a lower mu and it shouldn't. Where did we go? We had no mu's. Oh, it was alpha. That's what that was. Yeah, that's fine. Okay, that's absolutely fine. Okay, now we relabel them. So we swap the nu here. And that means that becomes a beta. Okay. Nu beta, nu beta. And then on this term is mu's. So I'll swap them for betas. Yeah, that's what I wanted. Okay, almost there. So now we have that this expression over here is equal to 2 second derivative. So let me write out, get rid of the dots now. So dx nu d lambda squared g alpha nu plus, then I want to make all of these the same, which they are. The betas and the nus are all the same. So I can pull them outside. Dx beta g lambda dx nu lambda, and then we have 3 terms: this term, this term, and this term. So we have d nu g alpha beta plus beta g alpha nu minus d alpha g beta nu. And that's all equal to 0. Okay, one last thing to do. I'll make space up the top. We're going to divide by 2 and do the same trick we did in the last lecture of multiplying by the inverse metric. Okay, so that completely gets rid of these from here. So then we're going to get plus a half. Now, we have to be careful with what index we go for. We'll say we multiply by g alpha mu. That would make that one up there mu, alpha mu. And then we get what's inside here. That remains the same. D nu g alpha beta plus d beta g alpha nu minus the alpha g beta nu. And then that's with dx beta, or x dot beta, x dot nu. And that's equal to 0. Well, what do we have here? These are nothing more than our Christoffel symbols that we had from the last lecture. So we've recovered the exact same equation we had earlier. D lambda squared plus Christoffel symbols with a mu and then a nu and a beta, and then we just have the x beta lambda dx nu lambda equals 0. That's the exact same equation for parallel transport that we had earlier. Pretty nice. Now, this thing that we did actually implied something much, much stronger. So we imposed, so our particles are ones that minimize the distance between the trajectories that extremize the distance along the paths. These paths are known as geodesics. So if we want our particles to satisfy this equation, then that implies that the Christoffel symbols must take this form up here. So what that does, it reinforces our choice of metric compatibility that we made in the last lecture as our sixth condition on the covariant derivative. It reinforces that that is equivalent to constraining our particles topology in the geodesics. So that's very cool to find out.